Hello everyone and welcome to this openCFS tutorial. In this video we will be looking at analysis types in openCFS. So the example problem we are looking at is a 3D cantilever beam which has a rectangular cross section, and we assume homogeneous isotropic material with linear elastic behavior, and we also consider small strains with geometric linearity. The beam is clamped at one end and a uniform pressure load is applied on top. So we'll start by creating the 3D geometry using Cubit, and we'll mesh it. And in openCFS, we'll see how to select an arbitrary monitoring point for writing outputs. And we'll also see how to add multi-sequence step like different analysis, static or harmonic or transient analysis, and also how to include mathematical expression, and of course our mechanic PDE. At the end, we will visualize the deformed geometry using Paraview. We'll load the multi-sequence results, and we'll visualize and animate the complex valued fields using Paraview. Let's have a look at our example folder. So we have 2.xml file for simulation and material input. We have a readme file, and we also have a beam.journal file for Cubit input. Let's have a look at it. So these are the commands used to create and mesh our geometry using Cubit. So let's open Cubit. We are looking at the Cubit GUI now. To create a geometry, select Geometry mode, Create Geometry, Create Volumes. Our beam has a width of 1.5, height of 0.1, and a depth of 0.05. Click Apply. This will create our geometry. The next step is meshing. So select Mesh mode, Volumes, and for the sake of simplicity we just specify the approximate size. So select our volume and specify an approximate size of 0.01 and click mesh. So this will create our simple mesh for our problem. The next step would be to create regions for boundary conditions. So select analysis groups and material, select node sets, and select create node sets. Now click the surface and select the surface you are going to fix. Give it a name, for example, yes, fix. Click apply, and then select the top surface for pressure load and give it a name S top. Select apply. The next step would be to create a block for material definition. So select blocks, select create material blocks, select create block, and then select our volume. So give it a name, for example V beam, and click apply. So now you look at our model tree. We have our node sets and the blocks which we have created. So let's export this mesh for openCFS input. So select file, export, and select answer CDB format and give it a name beam.cdb. So I'm just going to overwrite my previous file. Click save. And you can also save this geometry for future purposes. So click save, and you can save it as .cub file. So beam.cub file. So if you look at the folder, we have our .cdb file and beam.cub file, which we have created now. So let's go to our XML input. So let's have a look at our XML input. So we specify the input file, beam.cdb file, in our file format section, and here we also specify the output files, the HT5 file and the text file, and we also specify the material data file, which we will look into shortly. The next section is domain section, where we specify the geometry type, and we can also declare certain variables. So the important thing to remember is there are certain variables which are reserved for openCFS, like the spatial coordinates, time and frequency. So you need to be careful while choosing the variables. So the next would be to specify our material definition. We are using a material named alu, so which is defined in the mat.xml file. So here is our material alu, which has a density, elastic modulus and Poisson's number, which is enough for our linear elastic model. And here we also specify damping, which is necessary for our harmonic and transient analysis. So please have a look at the openCFS user documentation on how to specify damping input for different applications. So let's head back to our simulation input. The next important thing is so-called node list. Here we can choose the node which we are going to monitor. In our case, we are using this N node. So we specify the coordinates. So what CFS does is it picks the node which is closer to this coordinate point. So the next thing would be to start our analysis. So we specify the static analysis as sequence step 1. Here we have our boundary condition, a fixed boundary condition, and here we specify our load. So here we write certain results as output for post-processing. So please have a look at CFS user documentation on what kind of results you can write for different type of analysis and different type of PDE. So the next sequence step 2 is eigenvalue analysis. We write first 10 eigenmodes, and here we don't have a load because eigenvalue analysis has free undamped oscillation. So the sequence step 3 is harmonic analysis. Here we can specify the number of frequencies where you need the steady state solution, and also specify the start and the end frequency. And here we also specify the damping, which we declared in our mat.xml file. And the next sequence step 4 is transient analysis. Here we can specify the number of steps for the number of time step for transient analysis and the delta t. So the most important thing is here we specified the value, the pressure value, using a mathematical expression. So here we are using the variable t, which we have declared before in the variable list, and small t is a reserved variable, which is basically the time for our transient analysis. So let's have a look at how to use this XML to run our simulation using openCFS. So let's have a look at how to run the simulation using openCFS. So we have already exported our geometry as .cdb file, and we have already edited our mat and simulation.xml file. So to find the appropriate command for running simulation, you can look at the help menu by typing cfs -h. So we are going to use this command cfs -p and specify the name of our XML parameter file for simulation. So cfs -p simulation.xml and give the output a name like b, and this will start our simulation. So it runs all the sequence step, our static, our eigenfrequency, harmonic and transient analysis. So the simulation took a total of 1 minute and almost 4 seconds. So let's look at our folder. We have two new folders, history and result.ht5. So let's go to history, and we have two new files which are the output that we specified in our XML file. So if you look at the history folder, we have our deformed energy and also the mechanical displacement. Of all the sequence step, and also in the results.ht5 file we have our beam.cfs file which we will use visualize using Paraview. Let's visualize the results using Paraview. So open our output file, select our volume and select step 1 for static analysis result, click apply, and to visualize the deformed configuration, select warp by vector. So choose appropriate scale, and this will show the deformed configuration. And you can also select the plot the results you want, for example displacement or stresses and the components of stresses and so on. So yeah, this is our deformed and undeformed configuration. And let's plot the eigenvalue analysis results. So select analysis step 2, apply, and go to warp by vector, choose mechanical displacement real, and here you can choose mechanical displacement real also. So this will show our eigenmodes. Let's reduce the opacity. So as you can see here in this timestamp, we have all the eigenfrequencies, and you can step through and visualize all the eigenmodes by clicking this button. So this is our first bending mode, the second eigenmode, and so on. Let's plot our harmonic analysis results. So select analysis step 3, and to animate the results, choose animate harmonic / model results, apply, and you can also select the frequency step you want to plot. Let's select 12, apply, and go to warp by vector. So displacement, and you can run the animation by selecting the play button here. So you can also go to the animation view and select real time, and you can run the result in real time. So let's run it for 5 seconds. Let's see. Yeah, this is our animation for the selected frequency step. You can export this animation using the save animation option with whatever the file type you want. Let's visualize transient analysis result. So select step 4, apply, go to warp vector, mechanical displacement, choose appropriate scale. So as you can see in the timestamp, all our time steps are given here. So let's run it. To avoid this, you can choose appropriate scale, and yeah, let's run it. That is our transient analysis result. So let's run it again from the beginning for this time scale. Yeah, this is the result of the transient analysis. This can also be exported using save animation option. So yeah, this is how you can visualize different analysis results using Paraview. So thank you so much for watching this video, and see you next time.